Hello everyone, my name is Yuhao Zhou, and I am a PhD student from Northeastern University. Today I will talk about our work on language model guided TLA plus proof automation. This is joint work with my advisor Stavros Tripakis. So what is this talk about? As the title suggests, we developed an LLM guided method for automatically generating TLA plus proofs. The key idea here is to use hierarchical decomposition of proof obligations for doing the proof automation. I will explain what all of this means throughout this talk. But before that, let me start with some background on TLA plus proof quickly, just in case you are not familiar with it. Here is an example of a complete TLA plus proof module. The target theorem we are trying to prove is T1. It says that x plus x is even. We use L0 and L1 as intermediate lemmas to prove this obligation. For theorem L0, TLA PS will try to prove that automatically because it uses the obvious directive. And so do the L1. The TLA PS can prove that automatically by using this by-def directive. Once every theorem in this module is discharged, we know that the target theorem T1 is proved. And this is basically how a TLA PS proof looks like. Now, you might wonder how this compares to other theorem provers, especially the tactic-based provers like Lin. In general, the structure of TLA plus proof is different from the proofs written in tactic-based prover like Lin. On the left-hand side, you can see the TLA plus proof we just mentioned in previous slide. On the right-hand side, you can see the same theorem but proved in Lin. The Lin proofs has a sequence of tactics. Each tactic transforms the proof state step by step. The development of TLA plus proofs usually focus more on breaking down proof obligations into intermediate claims and steps instead of building a sequence of tactics like Lin. I also want to note that here, the TLA plus proof on the left-hand side can be written in a much simpler way. We write it in this form just for demonstration purpose. The distinction between TLA plus and the tactic-based proof here actually matters because in recent years, there has been progress in using LLMs to generate tactics for provers like Lin. But because of this type of difference in terms of the proof structure and the construction, such kinds of method that use LLMs as tactic generators cannot be directly and trivially applied to TLA plus proof automation. That is why we need new strategy for doing TLA plus proof automation leveraging AIs and LLMs. Now we have seen TLA plus proofs and how they differ from proofs in other provers. Let me define the problem we are trying to solve. So we would like to have a system that, given a proof obligation, along with the definition and the context, the system can then automatically produce a complete proof in TLA plus. In other words, the user provides theorem statements and the relevant context, and the system should be able to produce a complete proof in TLA plus that can be checked by TLA PS. So, how can we produce such proofs? Or how can we design such a system? Let me first discuss some naive method and see why they are not so sufficient. The first naive method is simply use the obvious keywords in TLAPS. The obvious tells the TLAPS to try to discharge the obligation automatically without additional informations. Essentially, we are just asking the prover, can you prove this on your own without any other help? For simple obligation, this works, and it actually works pretty well. But for complex proof obligation, it doesn't work. Usually, for complex theorems, it requires the user to provide additional hints to guide the prover. So if the symbolic prover alone are not enough for complex obligations, what about LLMs? The second naive method is to just use the LLMs to produce the entire proof in TLA+. We call this approach direct LLM-based proof generation, or DLPG for short. The high-level idea of this method is just to give the proof obligation to an LLM and then ask it to generate the entire proof directly in TLA+, and hope the best. It is not just a one-pass call to the LLMs. Instead, it has feedback loop. We give the proof obligation to the LLM as a part of the prompt. The LLM then generate a proof. We can then check it with TLAPS. If TLAPS accepts the proof, we are done. But if the TLAPS rejects the proofs, we collect the error message, compose it with the proof obligation, and then send it back to the LLM. Just let it try it again. We can repeat this procedure multiple times until the LLM-generated proofs is accepted by TLAPS, or we probably will reach a maximum number of retries, which means that there is no need to attempt more. Since there is a feedback loop between the LLM and the TLAPS, this gives the LLM multiple chances to correct its outputs based on the feedback from TLAPS. But DLPG runs into problems as well. The proof language of TLA Plus is a low resource language. There is no enough TLA Plus proof data available for LLMs to learn, especially during the pre-training phase. As a result, LLMs frequently generate proofs with incorrect syntax. They could mix the syntax from other proof systems, like Isabelle. For example, in this image and in our experiment, we saw that LLMs generating things like int arith, which is not a valid option in TLA+. In our experiments, even with error feedback from TLAPS, the LLMs still struggle to produce syntactically correct proofs. The feedback loop in DLPG can help, but it is not enough to overcome this problem. So now, both naive method does not work well. Obvious cannot handle complex theorems, and the DLPG struggle with the syntax errors. Let's take one step back. Think about how should we prove an obligation. We start with a proof obligation fee. There are two cases usually. First, the obligation might be easy enough, which means that if all necessary definition and assumptions are provided, TLPS can prove it directly. We built a tool named SAPG, which stands for Symbolic Auto Proof Generation. It analyzes the syntax tree of the TLA module, and then it collects all the necessary assumptions and definitions, and then based on that, it can construct the proof for the obligation automatically. This is a purely symbolic process without using any LLMs. So, if the obligation is easy enough, SAPG is able to prove it, we are done. But what if the obligation is not that easy? What if the SAPG cannot prove it? Then we need to decompose the proof obligation into smaller ones, just like the human would break a complex proof into intermediate lemmas or intermediate steps. Now the question is, how do we find the right decomposition? This is where the language models come in. We start with our proof obligation phi. Then we can ask an LLM to decompose the proof obligation phi into a set of smaller subclaims, P1, P2, and so on to the Pn. The LLMs use its reasoning ability to figure out what decomposition might be helpful to prove the obligation, and it will generate such a decomposition in terms of this P1, P2 to the Pn. And for each of the subclaim, we check whether SAPG can prove it. Some subclaims are simple enough and the SAPG can prove them directly. We check each of them, but some subclaims are still too complex for SAPG. For those ones, we go back to the LLM and ask it to decompose them into even simpler subclaims. And again, we check each new subclaim with SAPG. We keep doing this if we found something that SAPG cannot prove recursively until we find all the leaf obligation in this tree can be proved by SAPG. As you can see, the overall structure here is a tree where the root is our original proof obligation and the leaves are simple claims that SAPG can prove directly. At each level of this LLM-generated decomposition, we also check that the decomposition itself is valid. Specifically, we verify with TLA PS that the subclaims P1, P2, and so on, all these subclaims altogether actually implies the parent obligation phi. This is an important check because without this check, the LLM could generate subclaims that are individually provable but do not actually establish the parent obligation, which means this check ensures that we don't accept a wrong decomposition generated by LLMs. So to summarize our approach, if the obligation is easy enough, SAPG can prove that directly. If it's not that easy, we can decompose the obligation into smaller ones using LLMs. But remember the problem we saw earlier with the syntax errors? In this approach, the LLMs are responsible for generating the decomposition. And the LLM's output can also have syntax errors. So how do we handle this? Our solution to this is normalizing decomposition. Instead of asking LLMs to generate complete TLA plus proof, we normalize the LLM's output into a simple and structured format. Let me explain what this means. For decomposition, we could ask LLMs to decompose the obligation directly and let the LLMs generate an entire TLA plus proof module. But as we discussed, this often produces syntax errors because the LLM has to generate the valid proof syntax for the entire module. So instead, we asked the LLM to only generate structured and normalized decomposition which has minimum content. Specifically, the LLM will generate the JSON object. Each subclaims has an assumed field containing a list of Boolean expression and the proof field containing a single Boolean expression. This is a much simpler output format comparing to the entire proof module. The LLM only needs to express the logical content of each subclaim. Once we got this normalized decomposition, our system then can take it to construct the actual TLA plus proof automatically. In this approach, the LLM are constrained to only generate Boolean expressions, not the complete TLA plus proofs, so we get fewer syntax errors here. Now let me show you a concrete example of normalizing decomposition. Our proof obligation is here. We ask the LLM to decompose this into normalized form. The LLM returns two subclaims as JSON objects. As you can see, each subclaim is just a set of Boolean expressions including the assumptions and the goal. Our system then takes this normalized decomposition and construct the valid TLA syntax. As you can see, the normalized decomposition exactly corresponds to the lemma L0 and L1. So putting things together, this is the complete picture of our approach. We use SAPG for simple obligation. We use the LLM guided decomposition to decompose the complex obligation. And we use the normalization to reduce syntax errors. Now the question is, how well does this method work? So let me show you the evaluation of this method. We evaluated our system on 119 TLA plus theorems from two sources. First, there are 93 mathematical theorems that we collected from mini F2F and ProofNet benchmarks. These are standard benchmarks used in theorem proving community, especially the AI-guided theorem proving community. But they did not have TLA plus versions, so we translate them manually into TLA plus. Second, there are 26 theorems collected from inductiveness proof of distributed protocols. This represents a more practical use case for TLA plus. With these benchmarks in place, let me describe what method we compared against. We compared four methods. First, we just used obvious for every proof obligation in the benchmarks. Second is the SAPG, which is the symbolic tools that analyze the syntax tree and construct the proof without using any LLMs. And the third one is the DLPG, direct LLM-based proof generation. As a reminder, this method iteratively asks the LLM to generate complete proofs based on the feedback from TLAPS. And the last one is LLM-GPA, or full system of LLM-guided proof automation. Now, both DLPG and LLM-GPA rely on LLMs, so the choice of language models matters as well here. For LLMs, we selected diverse range of state-of-the-art models, including open source ones and proprietary ones. This includes Claude 3.7 Sonnet, DeepSeek 3.2 AXP, Gemini 2.0 Flash, Gemini 2.5 Flash, O3 Mini High, and GPT-5. All of these models were used without any fine-tuning. We rely entirely on prompting to guide these pre-trained models. And we also set the temperature to 0 for deterministic result. So with this model and the benchmarks, let me show what we found. Let's first look at the proof success rate, which is our primary measure of effectiveness. Here are the results in the table. Across all the benchmark and all the LLMs, we can see that LLM GPA consistently outperforms all the baselines. Let me walk through some specific numbers. For the mathematical benchmark, LLM GPA with DeepSeek proves 59% of the theorems, but the DLPG with the same model only improves 29%. With Gemini 2.0 Flash, LLM GPA proves about 55%, but the DLPG with the same model only improves 4%. And for O3 Mini High, DLPG proves 0% of the theorems, but the LLM GPA still managed to prove more than 50%. For the distributed protocol benchmark, we observe a similar trend. Most DLPG configuration proves very few theorems, often 0, but LLM GPA reaches up to 50% successful rate with DeepSeek model. So LLM GPA consistently performs better than DLPG in our experiments. One of the reasons is that the syntax error problem we mentioned earlier. Let me show you the data on that, the syntax error. This table compares the syntactic validity of LLM generated content between DLPG and LLM GPA. I want to note that for DLPG, we measure the syntactic validity for the complete proof, but for LLM GPA, we actually measure the syntactic validity for the decomposition. Because in both cases, this is the only content that the LLM is responsible for generating. Let me point out some numbers here. In DLPG, syntactic validity is relatively low. For Gemini 2.5 Flash, less than 1% of the generated proofs are syntactically valid. For O3 Mini High, it only has 0.2%. Even for the best model, Cloud 3.7 Sonnet, it only reaches about 20%. In contrast, with LLM GPA and our normalization strategy, syntactic validity is much higher. DeepSeek and GPT-5 reaches more than 85%, and the lowest, Gemini 2.0 Flash, still reaches more than 60%. This confirms that we can reduce the syntax errors by constraining LLMs to generate only normalized decomposition instead of the full TLA proofs. So to put everything together, our approach improves both the proof success rate and the syntactic validity of LLM generated content. Let me now conclude. We presented a recursive LLM guided decomposition approach for TLA plus proof automation. Our key prompting strategy is to constrain LLMs to generate only normalized decomposition, not the full proofs. This allows us to leverage the reasoning ability of LLMs for discovering the proof structures. At the same time, we can reduce the potential syntax error. We also introduced a benchmark suite, including 119 TLA plus theorems covering both mathematics and distributed protocols. And our evaluation shows consistent improvement of our method comparing to all other baselines across 6 different LLMs. That's it. Thank you for listening.